Hi, we present a per-motion structure approximation algorithm that leads to faster and accurate pose estimation. It is an approach that addresses in particular the pose estimation with global motion methods. First, about our motivation for this research. The state-of-the-art structure for motion pipelines follow a two-step process. First, one obtains the global initial solution for all images. This is followed by a refinement stage, that is a bundle adjustment procedure. As long as the building of the initial solution is generally neat and pretty fast, the bundle adjustment runs on the entire structure, meaning that observations corresponding to all image correspondences are packed up in a single equation matrix. This is clearly a bottleneck as the memory consumption grows quadratically with the number of images. To overcome this, several solutions have been proposed. They all partition the problem and distribute it using hardware-dedicated algorithms or rely on purely software-based solutions. Our contribution aims at improving the computation efficiency by leveraging the heaviest component of the bundle adjustment, the structure. We assume that the initial motions were generated using a global approach, and therefore we have full access to the pair and triplet motions computed at that stage. We then make use of the relative motions to approximate the structure with few virtual points and use that structure as input to the bundle adjustment regime. Our algorithm is not competitive to the above-mentioned state-of-the-art. It shall be seen as a module that can be combined with the state-of-the-art approaches at a pre-processing stage. Here's an example result of the approximation algorithm. On the left we have the full structure in 3D, reconstructed from several images taken around a courtyard. On the right we have the same result using our approximated structure, marked in red. We can see that the size of the structure on the right-hand side is significantly smaller, which directly results in 5 times faster processing times without significant accuracy loss. How do we achieve this? The preliminary step is to compute the relative motion between pairs and triplets of images. However, due to time limitation of this talk, I will not discuss that step in this presentation. Let's proceed directly to the structure approximation algorithm. Here's an example of the structure approximation from a single pair motion. The cameras are the 2 frustrums marked in green and red. The black points are the point correspondences constituting the full structure, and the 5 red points are the generated virtual points. How do we go about this? We start off with the full structure. On the right-hand side you can see a 2D toy example illustrating the flow. Once the points are intersected in space, we calculate their mean and covariance metrics. To give less significance to points that were intersected with larger projection errors, or small base to height ratio, we employ a weighting function that penalizes both. It is denoted as PDS. Given the covariance matrix K, we retrieve its eigenvalues and eigenvectors. The eigenvalues and eigenvectors correspond to the ellipsoid in 3D or an ellipse in 2D inscribed in these points. Note the figure in the right that illustrates the ellipse in red and the 2 eigenvectors in black. Finally, with the help of eigenvalues noted with small e and unit eigenvectors noted with capital E, we generate new virtual points. Here, the capital H corresponds to the coordinates in the coordinate frame of the relative motion, whereas the small h are the coordinates in the frame of the eigenvectors. To generalize this equation to 3D, we add the 3rd eigenvector. Now, the only question remaining is how to sample the space within the ellipsoid to get the virtual points. We have decided on 5 points distributed symmetrically because it is the sufficient number of points for several direct estimation algorithms. This configuration is presented in the bottom right corner of this slide. The new points are marked in green. The point number 4 with coordinates 0, 0, 0 is at the center of gravity. The remaining points are sent to 4 corners of the frame defined by the unit vectors. Let's move on to the experiments. To evaluate the algorithm, we use the following pipeline. We first extract the image correspondences with SIFT. We then build the relative motions. We approximate the structure using pairs and triplets. We then compute the global motions with the SFM init proposed by Wilson and Snavely, and when SFM init failed, we use the approach available in MICMAC. Finally, we run the bundle adjustment on all camera poses and image correspondences, and compare our results to the ground truth data as well as other solutions in terms of accuracy and runtime. We evaluate the approach on 3 datasets. First is the Steha benchmark consisting of 6 acquisitions. The number of images in all 6 acquisitions is small, but we decide to use it as it is a highly recognized benchmark in the computer vision community. The result presented corresponds to the acquisition with the highest number of images, 30. The table contains accuracies in millimeters, calculated as the differences between the positions of the resulting perspective centers and their ground truth positions. The initial solution provides a solution that is quite far from the true solution. CalMAP and MICMAC, which implement sequential structure for motion, converge to a 15 mm and 11 mm accuracy, respectively. Bundle adjustment run on the SIFT full structure as well as on the approximated structure converge to 30 mm. The runtime of our approach turns to be 5 times faster for this particular dataset, and the ratio between full and the approximated structure is equal to 19. You may ask yourself why the compression factor is not equivalent to the runtime gain. We explain it by the size of the dataset. The bundle adjustment setup operations, independent of the processing itself, take time that for small datasets is in the order of magnitude of the total processing time. You will see later that for larger datasets and longer processings, the setup time becomes insignificant and the runtime gain approaches the compression factors. Another dataset comes from a mobile mapping platform. It is composed of 647 images taken with a single fisheye camera looking in front of the car. The red points in the figure are the cameras and are surrounded by the 3D structure. The car drives in circles around the same block of buildings, which allows us to build the ground truth by exploiting the loops. In our tests, however, the algorithm is unaware of the loops. The figure illustrates the drift error for state-of-the-art in our approach. The SFM init did not succeed in finding the initial solution. We suppose it is due to the fact that it considers only pairwise motions, while the scene is quite challenging, with outliers in correspondences and a rather poor overlap between images. We resort to MICMAC to obtain the initial solution. The visible high-frequency fluctuation is due to the cyclical nature of acquisition geometry. Let's concentrate on the maximal values only. In red is the result of CalMAP, in green MICMAC, and in magenta the result with approximated structure. The latter places between CalMAP and MICMAC as far as accuracy goes. However, if we look at the runtime of the bundle adjustment with the full and approximated structure, you observe a 30 times faster computation. As you see, here with over 600 images, the runtime gain approaches the compression factor. Finally, the last dataset representing a classical UAV flight with 73 images and good overlaps. The SFM init again failed to find a solution. We resort to MICMAC to get the initial poses. As before, the table presents accuracies in millimeters computed in perspective centers. The initial solution is already pretty good, with an average of 41 millimeters. CalMAP and MICMAC converge to solutions as accurate as 18 and 27 millimeters respectively. The bundle adjustment run on the full structure results in 30 mm accuracy and the bundle adjustment on the approximated structure performs as good as COMAP, giving 17 mm accuracy. Concerning the runtime, the bundle adjustment on the full structure takes 8 times longer than the bundle adjustment on the approximated structure. To conclude, although not discussed in this presentation, we proposed a framework to calculate the relative motion on pairs and triplets. Secondly, to speed up the ultimate bundle adjustment routine, we introduced a way to abstract the pair motion 3D structure and its respective image correspondences, such that the estimation accuracy is preserved. Comparing against the state-of-the-art and the ground truth, we showed that running bundle adjustment on our approximated structure effectively refines the initial solution at a low computational cost. Thank you very much.